So we're going to prove this number. We're going to be proving in total 4 problems today, and this is the first one. So 87, prove that in the real numbers with the usual metric, a monotone sequence is a sequence that's only increasing or decreasing, perhaps because it is too monotone and cannot flirt. So we're going to be proving this. Here are a couple of the definitions that we're going to need in order to prove this. And since we are trying to show that something cannot happen, we're going to try to prove it by contradiction. And we have chosen our sequence to be 1 over n because we can see that this is a monotone sequence. It goes, if we choose n to be 1, then it is 1 over 1. Choose it to be 2, then it's 1 over 2, which is right here, and then we keep going 1/3, 1/4, 1/5, 1/6, and then all the way. As we can see, it is going to be approaching 0. Not quite reaching 0, but it will be approaching 0. And so we can tell that it has a limit of 0. And so let's proceed with our proof right here. So take the sequence x of n equal to be 1 over n to be a monotone sequence that flirts. And we can see again that the limit, as n approaches infinity, the sequence approaches 0. Thus, x sub n is a monotone sequence that decreases So this is where we're going to be applying our definitions. I have written the goal over here. X sub n cannot flirt. And the definition of a flirting sequence has to fulfill these requirements right here. Or, well, the opposite of these requirements. So this is the definition of what it means to flirt right here. We're trying to show that it doesn't flirt, so we want to see that n is not greater than n. And also, because we're trying to show n is not greater than n, eventually, right here, this has to be not less than the p sub n, the distance from p sub n all the way to whatever we're trying to reach is not less than the distance between p sub n all the way to, again, that point. So let's continue. So we know that there exists an x in the real numbers coming from this definition, and that such that x sub n converges to x, right? Because we are actually right over here. So x sub n converges to x, and let's say that x is equal to 0, because that is the point that we're trying to approach, and that is the limit. So then, by definition, we have for all epsilon greater than 0, there exists a natural number n such that for all little n's greater than the natural number n, we know that x sub n being equal to 1 over n minus x being equal to 0 is less than epsilon. So here, right here, is the calculation of the distance between these 2 points, considering that 1 over n can be anything. And so we take, let's say, epsilon is equal to 10, because our condition here, epsilon has to be greater than 0, so 10 is greater than 0. And since we have taken a natural number n, we will name that natural number, we can say 1. So take an epsilon equal to 10, which is greater than 0, and a natural number, namely n. Namely n equals 1. So let us let n to be, according to the definition, little n has to be greater than or equal to big N. So let the big N be less than or equal to n. Let's say n is equal to 20. And also according to the definition, right here, n has to be greater than n. So we're going to say n is less than n. And let's pick a number, let's say 30. 30 is greater than 20, so it checks out. And since we're trying to approach 0 here, we're going to set p as equal to 0. And since our sequence x sub n, we know now that it flirts, since we have built this sequence to actually flirt, given the definition that we have. We're going to say, again, using this part of the definition, now using this part of the definition, we're going to say that d, p sub 20, all the way to p, so the distance between p sub 20 all the way to p is less than epsilon, which is equivalent to 0 is less than, so 1 over 20, since we have the sequence 1 over n, we're just substituting the 20 into the n. And p is equal to 0, so minus 0, since we're calculating the distance between the 2 points. And it is less than epsilon. So we have 1 over 20 is less than epsilon is 10, right here. So we have built that, and we're trying to fulfill now the second part of this definition. And so p sub 20, the distance between p sub 20 and p sub 30, here we have our n equals 30, all the way to p. This whole thing is equivalent to, again, 1 over 20 minus 0. And then we also have p sub 30 all the way to p is 1 over 30 minus 0. And now we have 1 over 20 is less than 1 over 30. We know for a fact that 1 over 20 is not less than 1 over 30. So this is a contradiction. And since we now have found a contradiction, then we know 1 over 20 is not equal to 1 over 30. Thus, p sub 20, the distance between p sub 20 is not less than the distance between p sub 30 all the way to p. So, n cannot be greater than n. And there we go. Let's check everything out. So we have an epsilon greater than 0. We have a little n in naturals such that n is not greater than n, which is right here. And we have proven that this is true right over here. And we have shown that this is what we're trying to get to, and we have it right here. So, as a conclusion, a monotone sequence cannot flirt. Because again, flirting means it goes from one point, for it to get to, trying to get to that point, it gets closer to that point and then goes farther again and then closer again, but eventually in the end it never reaches that point. But in a monotone sequence it is either increasing or decreasing, so eventually it's going to arrive to whatever point we're trying to calculate the distance from. Okay, so let's move on to our next problem. Here we have a 92. In the real numbers with the usual metric, if two sequences flirt with 0, It froze. There we go. In the real numbers with the usual metric, if two sequences flirt with 0, does the sum of the two sequences flirt with 0? And we're trying to prove that it does flirt with 0. So that is our goal. And again, the definition of flirting sequences, it's right over here. So eventually, since we're trying to show that it flirts, the sum flirts with 0, we want to show that all of these check out. So let's try to build our sequence that flirts, two sequences that flirt with 0, so we can show that the sum of them also flirts with 0. So let's let sequence x of a equal to, I don't know, like 2 minus 1 over a. And x of b is sequence to be 1 over b plus 1. So we're trying to say that x of a and x of b both flirt with 0, such that since we have fractions here, we have to clarify that the values of a and b have to be natural numbers. And so let us take an epsilon 1 and an epsilon 2. We're trying to fulfill this part. Epsilon 1, epsilon 2 to be greater than 0. And right here we're trying to show that something is greater than a or b, which is n. So let's take a value. For example, suppose epsilon 1 is equal to 5 and epsilon 2 is equal to 10. The value doesn't matter, we're just trying to give an example. And then n being greater than a or b, we have to make sure that n is greater than a or b, or we pick a number that's greater than the numbers that we pick for a and b. So let's say m is 4, is 1 definitely smaller than n, and 2 definitely smaller than n. And we're trying to say that it flirts, we're trying to see if it flirts with 0. We're trying to build actually the sequence to be flirting with 0, so we want p, our final point, to be 0. And so, since the sequences a, x of a, and x of b flirt with 0, we want to show that their sum, so x of a plus x of b, also flirts with 0. And for us to show that, we are trying to show that it flirts with 0, so we want to show that by contradiction. Because again, we're trying to show that something happens by proving that it cannot not happen. Okay, so we will assume the opposite. Assume x sub a plus the sequence x sub b does not flirt with 0. So then, using this definition up here one more time, we're trying to find an epsilon that is greater than 0. So then for all, since we're adding the sequences a and b, for all epsilon name, let's say epsilon is equal to epsilon 1 plus epsilon 2. Greater than 0, there exists an a and a b, such that you know m is less than a or b. This is what it means to flirt using these definitions right here, with the definition right here. And for us to show it does not flirt, we have to use the opposite here. So we want to show that n is actually less than rather than greater than a and b. So for all epsilon greater than 0, there exists an a and b such that m is less than a or b, such that again 0 is less than the distance between p sub a, oops, I forgot the d, the distance between p sub a and p sub b, my bad, all the way to So the distance between p sub a plus p sub b and p, it's confusing, is equal to epsilon. Again, looking at this definition. And so we want to show now this part of the definition, that the distance between p sub a plus p sub b is greater than the distance between p sub n and p because of this part. And so we'll say 0 is less than, again, the distance between p sub a plus p sub b, and it's less than epsilon. We know that epsilon is equal to epsilon plus 1 and epsilon plus 2. And we also know that, well, we have said that a is equal to 1, b is equal to 2. So we're going to let p sub 1 plus p sub 2. So the distance between p sub 1 and plus p sub 2 and p, which is equal to 0, right here, is less than epsilon 1 plus epsilon 2. Now we do the distance calculation. So let's see, what's our first sequence? So we have this one, x of a, 2 minus 1 over a. So we have 2 minus 1 over n of a is 1. So this is just 1. This is just 1. And then we're going to add p sub 2, which is 1 over b. Oops, 1 over b. b is 2 plus 1 minus 0, because that's the other point we're trying to find the distance between. And we have epsilon 1 is 5, and the second epsilon we said was 10. Alright, so 2 minus 1 plus 1 half plus 1, these cancel, so we have 2.5 is less than 15, and that is indeed a fact. We also want to show again the second part of the definition. So let's see, the distance between p sub a plus p sub b and p is greater than d, the distance between p sub n and p. So again, we're just going to repeat all of this calculation over here. Plus 1 half plus 1, 0, is cancel, so 2 and 1 half. And we have 4. We said n is equal to 4 right here. So 4 minus 0 is greater than 4, which is a contradiction. So we have found a contradiction. We know that the sequence of x of a plus x of b, or the sum of these two sequences, flirts with 0. So to conclude, therefore, the sum of two sequences that flirt with 0 also flirts with 0. Right. Let's move on to our next one. So we have So we have 97, show that the real numbers minus 0 is not complete. So we are given a hint give a Cauchy sequence that does not converge within this space. We're trying to prove that something is not complete. So we're going to try to show that it is complete. And then if we see a contradiction within that, then we know that it in fact is not complete. So we are going to prove by contradiction. So again, proving by contradiction, suppose or assume the opposite. So suppose that the real numbers minus the set 0 is complete. And we have our goal over here. We're trying to show that something is complete, so we're going to be using the definition of what it means to be complete. And up here it says a complete space is a metric space where any Cauchy sequence converges within the universe. So, using that definition, we want to show that the sequence x sub n, the random sequence we chose, it is Cauchy, and that it converges within the universe. Well, we're trying to prove by contradiction, so I said that it doesn't converge. This is our ultimate goal right here. And equivalently, using this definition, for a sequence to be Cauchy, we have to show that this is true, such that this is true, and that it converges, or we're trying to show that it does converge, or it doesn't converge. And since we're doing contradiction, we're trying to show that it does converge within this proof, and then we're going to try to find a contradiction within that proof. So eventually, we're trying to say that it doesn't converge. So we're supposing that this is a complete space, hence there exists a sequence that is, again, Cauchy, such that x sub n converges to x. And so let's choose an x sub n sequence. So let's let the sequence to be x sub n. So let's take an r that is greater than 0. So we're trying to show that it is Cauchy. We're trying to build this sequence. We know that the number, really random number, is in the real numbers. That is our universe. And by the Archimedean principle, there exists an n such that 2, that is greater than 2 over r. And now we will let, in this part of the definition, we will let n and then be greater than or equal to n, where this is going to be a pretty lengthy one. 1 over n, right, minus 1 over n. So the distance, oops, not really distance, sorry, trying to show the retrieval in the column here. So the 1 over n plus 1 over n over here, because it is an absolute value, and this is equal to just 1 over n plus 1 over n. And again, we're trying to show that this is less than or equal to, trying to say that it's less than or equal to 1 over n plus 1 over n. And so we have 2 over n, and it's less than 2 times r over 2. And we cancel. So it's equal to r. Thus, 1 over n minus 1 over n is less than r. So there you go, the distance right there. Trying to show that the distance between x of n and x of m is less than r. And here we got it. So our sequence 1 over n is a Cauchy sequence in our complete space. So since we have a complete space and the real numbers minus the set 0, then using this definition right here, we have shown that it is Cauchy, so we now need to show that it converges. So for all g's and tau, so for all open set g, where the element x is in g, there exists a natural number n, big N, such that for all little n that is greater than or equal to the big N, x sub n is in G, or otherwise is in the open set. So as the value of n increases, we know x sub n approaches 0, and we have shown that earlier too in our previous problem that we had. X sub n, the limit of 1 over n as n approaches infinity is 0. However, 0 is not in our complete space. And proof right here is we have the real numbers, everything in the reals except for 0. So x sub n equals 0 is not in G. Therefore, x sub n being 1 over n, does it converge to 0? No, it does not. So x sub n being 1 over n does not converge to x. We have found a contradiction. Therefore, the real numbers minus the set 0 is not complete space. And we have shown all of these in our goal. So we said x sub n is Cauchy right here. And then we said that x sub n does not converge to x. And there we go. Let's move on to our next one, our last problem. This is going to be a relatively short one. So we have here 102. Let x sub n, the sequence, be a Cauchy sequence inside a complete space. If this sequence is outside of an open set, prove that the sequence converges to a point x outside of the open set. I have drawn a picture here just so we can visualize what's actually happening or what it wants us to prove, and by who it wants us to prove. So we have x's outside of an open set. And so x sub n is the sequence that is outside of our open set. This is our open set G. And x sub n being outside, we're trying to show that it converges to a point x. So we're trying to see if this is actually going to happen because we are proving by contradiction. Because again, in order for us to show that something happens, we have to, or something, yeah, we have to show that it cannot not happen, right? So let's suppose that x is in G, or the element x that later on we're trying to see if the sequence converges to is in the open set G. So suppose x is in the open set G such that G is open. So assume we're just trying to show just trying to choose any letter, any set. So assume E, let's say E is a complete space. So let x sub n be outside of an open set. Outside of an open set, right here, this is our thesis. Hence, x sub n, we know because it is outside, it is not in G, the open set G. Since x sub n is Cauchy sequence in E, right here, the definition of complete space. So complete space is a metric space where any Cauchy sequence, so we're trying to show that the sequence we have is Cauchy. We know that there exists an X in our complete space E, such that we're trying to show that the sequence converges within the universe, such that X sub n converges to X. Thus, by the definition of convergence, there exists a natural number n, big N, such that for all little n greater than or equal to n, x sub n is in G. And we said right here x sub n is not in G because it is outside of an open set. Then now, by the definition of convergence, which is right here, we said x sub n is in G. So what is this? This is a contradiction. Let's write that quickly. So we know x sub n is outside of an open set. Then x sub n converging to x means x cannot be in the open set G. And there you go. That concludes our problems for today.